Let us start today's session. In previous session, we had discussed about our transformations, and we have solved few problems on transformations, geometric transformation, very to be very precise. Homogeneous coordinates, the necessity of homogeneous coordinates, and why we need the homogeneous coordinates that we had discussed. Now, in today's session, we will be discussing few more concepts of geometric transformations. So, we'll see one of the most important form of transformation in which we have to mirror any entity about the line whose equation is given as y is equal to mx plus c. Okay, so about this line, we have to uh, reflect any entity. Fine. So this is one line whose equation is given as y is equal to mx plus c, and about this line, we might be having some entity. Let us say it's a point, it may be a triangle, it may be a square, whatever. Okay. So we need to reflect that entity about this line. So we cannot directly reflect this entity about the line. We have to consider the entity yes, if we consider and this is because we have the equations for the transformation matrices for reflection which are available, that reflection about x-axis, reflection about y-axis, or reflection about the z-axis. So we can reflect any entity about the principal axis only. Okay, so and defined as well. But if there might not be condition when we solve the when we encounter the situation that we have to reflect it about an arbitrary plane or an arbitrary axis apart from your principal axis. So for that we have to follow a few steps for the transformation. Now let us see what are those steps. And y is equal to mx plus c passes through the origin. Okay, so what we have to do over here, we have to translate this line or axis to origin, and whenever we translate this line or axis to origin, the entity which is associated with that line, that will also get transferred to the origin. Now for that we want the translation. Okay, since we are shifting the position of the line, we are performing the translation transformation. Now how much distance we have to transform the translate? So we have to translate the distance which is equal to slope of the line or y-intercept of the line, not slope, y-intercept of the line. The y-intercept is defined by this c. Okay, so let us say the equation of the line is 0.5x plus 3. So the 3 plus 3 is the y-intercept, and that distance is this. Okay, that distance is this 3 units or c units. So we have to translate this line to origin. Now the translation distance will be tx is equal to 0, since we don't have to make any changes in the along x direction, but we have to shift this line to origin, so that we'll be making the y-intercept as uh, minus c. Minus c means let us say if it is plus 3, if we make it minus 3, then this line will passes through origin, which is shown with the help of dashed line. So our translation matrix, translation transformation matrix will be 1 0 0 0 1 0 and tx ty 1, which is our regular translation matrix. But in this case, it will be tx value will be 0 and ty value will be minus c. Okay, so it is the case, one of the situation when the y-intercept is positive. If the y-intercept is negative, let us consider this line as over here. Okay, so this is the, if we extend the line over here and this line is over here. So your y equation of the line is equal to y is equal to 0.5x minus 3. So the y-intercept is, in that case, it is your minus 3. So somewhere over here, your line is going to pass. So if you want to translate it to origin, this minus c will be plus c in that case, if your y-intercept is negative. Okay, so first step is translation. You have to translate the line and the given entity such that the line y is equal to mx plus c passes through the origin. It will pass through origin, and for that you have to perform the translation transformation, making necessary changes in the y-intercept which is given in the equation of the line. Fine. Now, once this line is passing through origin, we have to rotate this line and the given entity about the origin until it coincides with the x-axis. Now we have to, second transformation we have to perform is, we have to rotate this line and the given entity until it coincides with the x-axis. Fine. So now, why you might have guessed that why we have making all these changes, because we have the equation or the transformation matrix for reflection along x-axis, y-axis and z-axis only. So here we are making our adjustment so that we can use that particular transformation matrix for the reflection. So we are rotating this line and an entity about or the origin so that it will coincide with x-axis. Now for that we need the angle of rotation. Now that rotation angle theta can be found out as tan minus tan inverse of m. So where m is your slope of the line, which you can get from the equation of the line. From over here you can get the value of m and you can find out the theta. Now it is important to note that angle theta will be negative since the rotation is clockwise direction. Okay, so going back, if you can see that over here we are rotating the line such that it will coincide with the x-axis. That's why the rotation is clockwise, and as far as our conventions are concerned, we can take the angle theta as negative since the rotation is in clockwise direction. Right? So we use this rotational formula, cos theta sin theta minus sin theta cos theta 0 and 0 0 1. If the rotation is clockwise, you will be taking this theta as negative. Now after rotation, you can see that the line is now coinciding with the x-axis. Okay, previously the line was over here. We have translated it so that it will pass through origin, and then we have rotated it so that it will coincide with the x-axis. Now we can reflect the entity, any entity which is associated with the line along that line and along that x-axis, since the line and x-axis are coinciding. So we use along x-axis, reflection about x-axis, the transformation matrix as 1 0 0, 0 minus 1 0 and 0 0 1. Okay, now our job is done for the reflection of any entity about the given line. Fine. Now, but the line was originally not coinciding with the x-axis. It was somewhere over here, having some y-intercept and having some slope. So for that, what we will be doing after step number 3, we will be repositioning the line. We will positioning the line from where it had it was located previously, we are trying to shift the line over there only at its initial position. So for that, we have to take inverse rotation. Okay, we have to take the inverse rotation. Now we are rotating the line by an angle theta. Now don't get confused, since I haven't written minus theta over here and I am writing minus theta over here. It is just for showing you the sign convention. It is just for showing you the difference between your rotational transformation and inverse rotational transformation. So in rotational transformation, we write cos theta sine theta. But if we are trying to write the inverse of this matrix, rotational matrix, we will write cos minus theta minus sine minus theta, etc. Okay, but whenever you encountered with the physical problem, we will be writing this theta as negative because the rotational direction is a clockwise direction. Okay, and in inverse rotation, we will be writing it as positive, which will be exactly reverse of the rotational matrix. Okay, so this point will be more clear when we solve few problems. So we are making it inverse rotation. Okay, so the line is now rotated with some angle which we have found out over here, and now the line is passing through the origin. And the last step is inverse translation. Now since the line is now passing through origin, we have to shift it at some intercept, y intercept. So we're making it minus tx minus ty. So tx we take it as 0, and minus ty we take it as plus c. Now it is 0, and we are translating it by distance c. Let us say for y is equal to 0.5x plus 3, we will be translating it by 3 units. And in the first step, we have translated it by minus 3 units so that it will pass through origin. That changes we have made. And then if we want to find out the concatenated transformation matrix, your final answer will be multiplication of step number 1, that is translation, step number 2, rotation, step number 3, mirror or reflection, step number 4, inverse rotation, step number 5, inverse translation. All these matrices that we have formulated in making the reflection to be done, all these matrices has to be multiplied, and then we will get the concatenated transformation matrix. So that is what we call composite transformation matrix also. So the definition of concatenated matrix transformation matrix is that the matrix which consists of more than one transformation. That matrix is called as concatenated or composite transformation matrix. So here we are having 5 transformations, so that's why it is called as concatenated transformation matrix. So once you find out the concatenated matrix, if you want to find out the original coordinates or the new coordinates of the any entity, so you have to multiply it with this concatenated transformation matrix with your original coordinates, and you will get your new coordinates of the matrix. Let us say P is the point which we have to reflect it, and which is given by some xy coordinates. So that coordinates in matrix form is to be multiplied to this concatenated transformation matrix, so that you will get the new coordinates of the that point after reflection about any arbitrary axis. So let's take a recap. We are trying to find out the sequence of transformation which is to be made to mirror any entity about the line, whose equation is given as y is equal to mx plus c. We need these sequences. The reason is we cannot reflect any entity about any arbitrary line or any arbitrary axis, since we have the transformation matrices for reflection available only for coordinate axis, that is x, y, and z. So we have to make the necessary changes. So we will be translating it, translation transformation. For that we are using the y-intercept. We are making the y-intercept so that the line will pass through origin. We'll make the changes in y-intercept, and that ty will be minus c. Okay, it is minus c because the line is in positive axis. If it is in negative side, if the y-intercept is negative, we have to take it as positive. Fine. Don't worry, we'll be solving one problem on this also. So first is this, the line is passing through origin. Second, we are rotating the line in such a way that it will pass or it will coincide with the x-axis. For that, we need the angle of rotation, which we can find out by theta is equal to minus tan inverse of m. Uh, the value of m will be getting from the equation of the line. The angle, the sign you need to take care of angle. If the rotational uh, direction is clockwise, we have to take this angle as negative. Okay, so first axis we will be taking as negative, then we will be reflecting it about x-axis, fine, and after reflection we will be repositioning the line and the entity to its original position. So for repositioning, we will be again inverse rotating this line. For that, we'll be making use of minus theta or the inverse of the rotational transformation matrix, which we have used in step number 2, and we'll be then translating it inversely. When we multiply all these transformations by transformations, we'll get the concatenated transformation matrix. When this concatenated transformation matrix is multiplied with your original coordinate matrix, you will get the new coordinates of the entity after reflection. Fine. So this is the theory part. I mean, this is the sequence of transformation that is used to reflect any entity about any line whose equation is given to us. So this is very important as far as examination is concerned. Most of the time they ask you such kind of questions, and that to be in a twisted manner. So there are a lot of scope to ask the questions on this kind of sequence of transformation. Let us see a few examples. First, a triangle PQR with vertices P2, 5, Q 6, 7, and R 2, 7 is to be reflected about a line y is equal to 0.5x plus 3. So here we can say that value of m is zero point 0.5 and value of c is plus 3, which we are making use in our transformations. Then we have to determine the concatenated transformation matrix. This matrix we have to determine, and the vertices of the reflected triangle. So after reflection about this line y is equal to 0.5x plus 3, what will be the new coordinates of the vertices of a reflected triangle, that we have to find out. Okay, so let us start with the solution. And step number 1, translation. First, we have to translate this line so that it will pass through an origin. Okay, for that, what we have to do, we have to shift its y coordinates, match its y coordinates to 0. So here y coordinate or y intercept is plus 3. We are making that y intercept as minus 3. Okay, so y intercept of the line is 3. We are making it as minus 3, so that your line along with the entity will pass through the origin. So our translational transformation matrix is 1, 0, 0, 0, 1, 0, dx, dy, and 1. Okay, so dx, we are not saying anything about dx because nothing to do with the x-axis or x-intercept. On the y-intercept, we have to make it as minus 3. Once we make it minus 3, your line and your entity, the line is passing through origin, and your entity is also translated by that much of distance. So this is first transformation, translation. Second, rotation. Now for rotation, we want the theta. Okay, so for theta, we want m. So minus tan inverse of 0.5. So this is the m value we are using, and this is y is equal to 0.5 plus 3, mx plus c, m is equal to 5, and we get the angle as minus 26.565. So we are taking is that as it is because our rotational direction is clockwise. Okay, here after this, we are rotating the line so that it will pass through, it will coincide with the x-axis, and this direction of rotation is clockwise. That's why we are taking this angle as negative. So this is important step. Most of the students make mistake over here. Cos minus 26.565 sine minus 26.565. In this way, we have written our rotational transformation matrix. Okay, so this is the after solution we get this as the rotational transformation matrix. So what happened? We have translated to the line so that it will pass through origin along with the entity, and we have rotated the line so that it will coincide with the x-axis along with the entity. Okay, now we will be reflecting it about the x-axis. Okay, so for that we have this transformation matrix, reflection transformation matrix, 1 0 0 0 minus 1 0 and 0 0 1. So this is for this step number 3 only we are doing all these exercises. So step number 3 we have performed, then we have to reposition it. We have to reposition the line and the entity to its initial position. So for that we have making use of inverse rotation. Okay, so we are rotating the line by an angle 26.565 so that the line will now passes through origin. For that we will be making use of 26.565. Now note here, since the rotation is clockwise, we are making made this, we are consider this sign as negative, but over here in inverse rotation we will be taking exactly reverse sign of the rotational matrix that we have used in step number 2. So for sign you have to take care over here only. Whatever the sign is available according to your direction of rotation, you have to consider that sign in step number 2 in simple rotation, and the exact reverse sign, opposite sign, you have to use in the case of inverse rotation. Fine. So here we are using cos 26.565 and theta with positive sign. So this is your inverse rotation. So we'll get this matrix. Now inverse translation. Now we'll be making repositioning the line where it was previously originally whenever in step number 1. Okay. So for that we have to make the y-intercept as whatever given in the equation of the line. So recall that in step number 1 we have used this ty as minus 3 so that the line will pass through the origin. Now to reposition it we will be considering this as plus 3 so that the line will attain its original position. So this is the matrix. Okay, 1 0 0 0 1 0 and 0 3 1. So we have found out, we have gone through all these 5 transformation, and now it's the time to find out the concatenated transformation matrix or composite transformation matrix. Composite transformation matrix is the multiplication of all these matrices in a sequence. Okay, in a sequence. In some literature, they have given that you have to find out the reverse sequence, like inverse translation, inverse rotation, then mirror, then rotation and translation. So remember, in some books it is given as reverse, but for those books they have manipulated these matrices also. Okay, so don't go by that method. Just stick to whatever I am saying to you, whatever I am presenting in front of you. Okay, so this is translation, rotation, mirror, inverse rotation, and inverse translation. When we multiply all these matrices, we'll get the composite or concatenated matrix. Okay, zero point 0.6, zero point 0.8 minus 2.5, 0.8 minus 0.64, 0.8, 0, 0, 1. This is your composite transformation matrix that you got after multiplying all these matrices. Now, I need not to tell you that this is your task to multiply, how to multiply. Okay, you may start from these two matrices or these two matrices. It's up to you how to multiply it. Okay, so this is concatenated transformation matrix. So answer number 1 is received, that this is a composite transformation matrix or concatenated transformation matrix. Now we have to find out the vertices of the new triangle. The vertices of the reflected triangle can be found out by concatenated transformation matrix multiplied by the original coordinates. If you look at the problem, coordinates for P, vertex P is 2, 5. Okay, so here we will be using 2, 5 and 1. 1 is the homogeneous coordinate. So when we multiply this concatenated transformation matrix to this original coordinates or the initial coordinates, we will get the new coordinates for the vertex. So 2.8 and 3.4 are the new coordinates for the vertex P. Similarly, for Q, if we multiply it by composite transformation matrix, and for R, if we multiply it by composite transformation matrix, we will get the new coordinates for the vertices Q and R respectively. So the new coordinates will be 2.8, 3.4, Q dash is 6.8, 5.4, and R dash is 4.4 and 2.2. So this is your answer number 2, the vertices of the reflected triangle. Where we have reflected the triangle, we have reflected the triangle about a line whose equation is given as y is equal to 0.5 x plus 3. Okay, so for that we have used the translation, rotation, mirror or reflection, inverse rotation and inverse translation. After that we have found out the composite transformation matrix multiplying all these transformation, and when multiply this composite transformation matrix to the original coordinates, we will get the new coordinates of the matrix. So this is one problem. The next one. A triangle ABC with vertices A 30, 20, B 90, 20, and C 30, 80 is to be scaled by a factor zero point 0.5 about a point x 50, 40. Okay, so we have given with one triangle with vertices, the coordinates of vertices are given, which is to be scaled by a factor zero point 0.5 about a point x whose coordinates are 50, 40. So scale by a factor zero point 0.5 means Sx is equal to zero point 0.5 and Sy is equal to zero point 0.5. If you recall my previous session, I told you that one scale factor indicates your original size. If the scaling factors are more than one, the object is enlarged, and if the scaling factor is less than one, your object is reduced. So here the scaling factor is 0.5, so your triangle will be reduced by half of its original size, and that too we have to scale it about a point which is given by x is equal to 50, 40. So about this point we have to scale this, we have to reduce this triangle. Now we have to find out the composite or concatenated transformation matrix and the coordinates of the vertices for a scale triangle. So what is given with us, Sx is equal to Sy is equal to 0.5. It's a case of uniform scaling since Sx and Sy values are same. Now we cannot scale any entity about an arbitrary point. We cannot scale anything about an arbitrary point. For that we have the scaling matrix, scaling transformation matrix for scaling about the origin. If we are scaling about the origin, then only we can scale the any entity. Fine. So for that, now you can guess what we have to do. To scale it, we have the scaling matrix about origin, and they want us to scale it about this x, arbitrary point x whose coordinate is 50, 40. So first we have to do is, what we have to do is, we have to translate this x point to origin. We have to translate this x point so that it will coincide with the origin, then only we can scale it. Got my point? So for translating it to origin, what we have to do, we have to make the distances tx is equal to minus 50 and ty is equal to minus 40. Now it is obvious that, let us say one point is there whose coordinates are 50, 40. If we want to coincide this coordinate, these coordinates are with respect to origin. If we have to shift it to origin, what we have to do, we have to make it as minus 50 and minus 40 so that it will coincide with the origin. Okay, so we'll be using tx is equal to minus 50 and ty is equal to minus 40 so that it will coincide with the origin. So this is first translation. Then we scale. Sx000 Sy00001. This is the scaling matrix for scaling about the origin. Fine. Now what we'll be doing, we'll be repositioning this point and the entity to its original position. Repositioning. We are making the repositioning. So for that, what we'll be doing, we'll be making minus tx and minus ty. So minus tx and minus ty means 50 and 40. Again, here you might get confused that you are translating over here and making it minus 50 and minus 40, and here you are writing 50 plus 50 and plus 40. So just for the sign convention, it is quite obvious that the distances traveled is minus 50 and minus 40 in regular translation, and exactly reverse we have to use in the inverse translation. Okay, so that's why I wrote over here minus 50 and minus 40 and 50 40 over here. These matrices are for the indicative purpose that this is your regular translation and this is your inverse translation. That's why I have put the minus signs over here, minus tx and minus ty. Minus sign indicate the inverse of the matrix for the translation. Okay, so we have made the inverse translation. Now we'll find the composite transformation matrix. Here the translational matrix, scaling matrix, and inverse translational matrix. Okay. So here it is minus 50, minus 40, 0.5, 0.5 Sx and Sy, and here plus 50 and plus 40. So this is your composite transformation matrix. When we multiply the vertices of the triangle composite transformation matrix by 30, 20, 90, 20, and 30, 80, all these are your original coordinates of the triangle. So here we have taken Hello, is my screen visible?
No, sir, no.
No, sir.
Just one second.
Yes, sir. Screen is visible.
It is visible now.
Yes, sir, yes. It is visible now.
Yes, sir.
Okay. So this is how we can solve this kind of problem. This is one type of problem in which you are scaling it about any arbitrary point, and the previous one was reflecting about axis. Now we'll solve one more problem, which is of another type. A rectangle ABCD having diagonal corner A 2 comma 2, then C 10 comma 8. These are the diagonal coordinates for the rectangle, which is to be reflected about a line y is equal to 1.7321x minus 3. You have to determine the concatenated transformation matrix and the coordinate of the rectangle after transformation. Okay. So first we'll write the coordinates, the diagonal corners as your in the matrix form. So 2, 2, 1 and 10, 8, 1. This is your matrix. Your equation of the line is y is equal to 1.7321x minus 3. Here y-intercept, note that your y-intercept is minus 3. That means exactly reverse of what we have discussed in the problem number 1. So that's why you have to translate it by plus 3. Okay, so as I mentioned in the problem number 1, the y-intercept is now over somewhere over here. So we have to translate it by plus 3 units so that your line will pass through the origin. You have to rotate it by minus theta and reflect it about x-axis and inverse rotation and inverse translation to get the mirror image. Now tan theta, if your slope is given as 1.7321, theta is found out to be 60 degree. Here I have found out it directly. Theta is equal to minus tan inverse of m. Now, as the rotation is clockwise, to make it align with x-axis, we take theta as minus 60 degree from the with reference to your problem number 1 or step number 1. So translational matrix 1 0 0 0 1 0 x we are not doing anything, and this is plus 3. Why? Because in the equation of the line y is equal to whatever m is given, x minus 3 is given. That's why we are making it as plus 3. Okay, and then we have cos minus 60, sin minus 60, 0, minus sin minus 60, cos minus 60 and 0. So this is the minus sign we are taking since we are rotating it in clockwise direction so that it will coincide with the x-axis. Then this is for mirror about x-axis. Then cos 60, this is inverse rotation, and here sorry, it is cut over here, but it is we are taking as minus 3. Okay, so since we are repositioning it, so multiplying all these matrices, we have this concatenated or composite transformation matrix that we have got, and after that we have to find out the new coordinates for the your what we can say diagonal corners of the rectangle. So this you can either multiply it by taking single corner or single vertex, or you can multiply it as a combined matrix. So 2 2 1 10 8 1 and multiply it, you will get the new vertices as 3.3 and 1.232, and b dash is equal to 4.526 and 11.16. So this is how this is one of the type of problem that can be asked. Here you are making your y-intercept as negative, and in the first problem the y-intercept is positive. So these are few ways to ask the problem, but the core of the concept is that we cannot mirror or we cannot scale any entity if it is not coinciding with the origin or if it is not coinciding with the coordinate axis. So for that we have to make the necessary transformation like translation. To make the necessary transformation, be in the position to carry out this particular reflection or scaling type of thing. So that's why we make all this stuff. So this is one important concept for solving this kind of problem. So this is all for today from my side. If you are having any question, please ask me. Yeah. So if there are not uh, question, then you can put your attendance in the chat box and you can log off.
Hello.
Yeah.
हॅलो सर लिव्ह केलं तर चालेल ना?
हा चालेल, सांगितलं मी.
ओके थँक्यू सर.
Mark your attendance and you can leave, log off the session.
येस सर आय डिड इट सर. थँक्यू.